Hi, my name is Rachel Jenkins, and today I will be explaining the Prins reaction. The Prins reaction consists of the addition of an alkene to an aldehyde through acid catalyzation. 3 different products can be formed through this process after the beta hydroxyl carbocation intermediate is formed. So first, the aldehyde must get protonated from a H3O plus molecule, which then creates the carbocation on the aldehyde. Then the alkene can come in an addition way and attack the carbon. Then the beta hydroxyl carbocation intermediate is made. This intermediate will then be the starting material in each of the 3 possible pathways. When no other reagents are present except for water, allylic alcohol is formed. The water will remove a hydrogen, and then that bond will form a double bond, which will then neutralize the product. H3O plus is also a byproduct in this. The second process is the formation of an alcohol. There's no double bonds. So a nucleophile will come in and attack the previously formed carbocation from the intermediate and then form that alcohol. The third way is when aldehyde is present in excess. The oxygen with the double bonds will come in and attack at the carbocation site and attach. Next, the oxygen will attack the more substituted part of the double bond, and then that double bond will get pushed up onto the oxygen and neutralize the positive charge. Then, through water, the other side has become protonated because it lost one of its lone pairs, the oxygen did. So the water will then neutralize that and create our product of 1,3-dioxane, and also another byproduct of H3O plus. To explain the reaction coordinate diagram, here is the reaction. So we have the starting products of our aldehyde and alkene, which are shown at the middle, and then we have more potential energy once the intermediate carbocation, the beta hydroxyl carbocation, is formed, and then once we have our either water nucleophile or aldehyde in excess, we can form our 3 different products of allylic alcohol, alcohol, and 1,3-dioxane. Each product is lower because the potential energy drops because it's an exothermic reaction. One example of this being used is to minimize a synthesis. So a one-step synthesis of octochromins was made possible, and the reactants used were chiral polyglyls and benzylaldehydes to produce this product in a way that certain stereochemistry could be favored. The Prins reaction was essential for this product being formed because it's commonly used to produce biologically active octo-2H chromin 4-OS products. One way to speed up this reaction is to use a more nucleophilic starting material or to increase the temperature. Both of these will increase the rate of the reaction, but also it's important to consider which product you want to form. The 1,3-dioxane has more steps in its synthesis, therefore it might take longer than the allylic alcohol and the alcohol. In the infrared, we are starting with an aldehyde and an alkene. So there would be a disappearance of the aldehyde at 1720 centimeters, 1 to the minus, and a disappearance of the alkene at 3100 centimeters, 1 minus, and then the appearance of an aromatic and also an OH group in the allylic alcohol and the alcohol group. For For the 1H proton environments, the aldehyde is very much downfield at 9 to 10, as is the alkene starting materials, and there is an upfield shift in each of the products being formed. So the 1,3-dioxane is moved to about 5, 4, and 2 ppm for its hydrogen environments, and the alcohol and allylic alcohol are also shifted upfield and have proton environments at about 1 and 2 ppm, several, and their peaks are a little differed. And then for the carbon environments, the alkene is downfield at about 160 to 120 ppm. The aldehyde is also downfield at about 180 to 200 ppm. And then as the products are formed, there is an appearance of an OH group, and the allylic alcohol and the alcohol, and there's the disappearance of the starting products, and then there's also an appearance of a ring group with the 1,3-dioxane, and that is it. Thank you.